Energy is the ability to do work. The average American has available the energy equivalent of about 150 slaves working 24 hours a day. Materials that store this energy for work are called fuels. Some fuels contain more energy than others. This is called energy density. Of these fuels, oil is the most critical. The world consumes 30 billion barrels a year, equal to 1 cubic mile of oil, which contains as much energy as would be generated from 52 nuclear power plants working for the next 50 years. Although oil only generates 1.6% of US electricity, it powers 96% of all transportation. In 2008, 2/3 of America's oil was imported. Most was from Canada, Mexico, Saudi Arabia, Venezuela, Nigeria, Iraq, and Angola. Several factors make oil unique. It is energy dense. 1 barrel contains the energy equivalent of almost 3 years of human labor. It is liquid at room temperature, easy to transport, and usable in small engines. To acquire energy, you have to use energy. The trick is to use smaller amounts to find and extract larger amounts. This is called EROEI, energy return on energy invested. Conventional oil is a good example. The easy-to-extract, high-quality crude was pumped first. Oilmen spent the energy equivalent of 1 barrel of oil to find and extract 100. The EROEI of oil was 100. As the easy-to-find oil was pumped first, exploration moved into deep waters, or distant countries, using increasing amounts of energy to do so. Often, the oil found now is heavy or sour crude and is expensive to refine. The EROEI for oil today is as low as 10. If you use more energy to get the fuel than is contained in the fuel, it's not worth the effort to get it. It is possible to convert one fuel source into another. Every time you do so, some of the energy contained in the original fuel is lost. For instance, there is unconventional oil, tar sands and shale. Tar sands are found mainly in Canada. 2/3 of the world's shale is in the US. Both of these fuels can be converted to synthetic crude oil. However, this requires large amounts of heat in fresh water, reducing their EROEI, which varies from 5 to as low as 1.5. Shale is an exceptionally poor fuel, pound for pound containing about 1/3 the energy of a box of breakfast cereal. Coal exists in vast quantities and generates almost half of the planet's electricity. The world uses almost 2 cubic miles of coal a year. However, global coal production may peak before 2040. The claim that America has centuries' worth of coal is deceptive, as it fails to account for growing demand and decreasing quality. Much of the high-quality anthracite coal is gone, leaving lower-quality coal that is less energy dense. Production issues arise as surface coal is depleted and miners have to dig deeper and in less accessible areas. Many use destructive mountaintop removal to reach coal deposits, causing environmental mayhem. Natural gas is often found alongside oil and coal. North American discovery of conventional gas peaked in the 1950s and production peaked in the early 70s. If the discovery graph is moved forward by 23 years, the possible future of North American conventional natural gas production is revealed. Recent breakthroughs have allowed the extraction of unconventional natural gas, such as shale gas, which might help offset decline in the years ahead. Unconventional natural gas is controversial, as it needs high energy prices to be profitable. Even with unconventional gas, there may be a peak in global natural gas production around 2030. Large uranium reserves for nuclear fission still exist. To replace the 10 terawatts the world currently generates from fossil fuels would require 10,000 nuclear plants. At that rate, the known reserves of uranium would last for only 10 to 20 years. Experiments with plutonium-based fast breeder reactors in France and Japan have been expensive failures. Nuclear fusion faces massive technical obstacles. Then there are the renewables. Wind power has a high EROEI, but is intermittent. Hydropower is reliable, but most rivers in the developed world are already dammed. Conventional geothermal power plants use existing hotspots near the Earth's surface. They are limited to those areas. In the experimental EGS system, 2 shafts would be drilled 6 miles deep. Water is pumped down one shaft to be heated in fissures, then rise up the other, generating power. According to a recent MIT report, this technology might supply 10% of US electricity by 2050. Wave power is restricted to coastal areas. The energy density of waves varies from region to region. Transporting wave-generated electricity inland would be challenging. Also, the salty ocean environment is corrosive to turbines. Biofuels are fuels that are grown. Wood has a low energy density and grows slowly. The world uses 3.7 cubic miles of wood a year. Biodiesel and ethanol are made from crops grown by petroleum-powered agriculture. The energy profit from these fuels is very low. Some politicians want to turn corn into ethanol. Using ethanol to supply 1/10 of projected US oil use in 2020 would require 3% of America's land. To supply 1/3 would require 3 times the area now used to grow food. To supply all US petroleum consumption in 2020 would take twice as much land as is used to grow food. Hydrogen has to be extracted from natural gas, coal or water, which uses more energy than is generated from the hydrogen. This makes a hydrogen economy unlikely. All the world's photovoltaic solar panels generate as much electricity as 2 coal power plants. The equivalent of between 1 and 4 tons of coal are used in the manufacture of a single solar panel. We'd have to cover as many as 140,000 square miles with panels to meet current world demand. As of 2007, there were only about 4 square miles. Concentrated solar power, or solar thermal, has great potential, though at the moment there are only a small number of plants operating. They are also limited to sunny climates, requiring large amounts of electricity to be transmitted over long distances. All of the alternatives to oil depend on oil-powered machinery, or require materials such as plastics that are produced from oil. When considering future claims of amazing new fuels or inventions, ask, does the advocate have a working commercial model of the invention? What is its energy density? Can it be stored or easily distributed? Is it reliable or intermittent? Can it be scaled to a national level? Are there hidden engineering challenges? What is the EROEI? What are the environmental impacts? Remember that large numbers can be deceptive. For example, 1 billion barrels of oil will satisfy global demand for only 12 days. A transition from fossil fuels would be a monumental challenge. As of 2007, coal generates 48.5% of US electricity. 21.6% is from natural gas. 1.6% is from petroleum. 19.4% is from nuclear. 5.8% is from hydro. Other renewables only generate 2.5%. Is it possible to replace a system based on fossil fuels with a patchwork of alternatives? Major technological advances are needed, as well as political will and cooperation, massive investment, international consensus, the retrofitting of the $45 trillion global economy, including transportation, manufacturing industries and agricultural systems, as well as officials competent to manage the transition. If all these are achieved, could the current way of life continue? These bacteria live in a bottle. Their population doubles every minute. At 11 a.m, there is one bacterium. At 12 noon, the bottle is full. It is half full at 11:59, leaving only enough space for one more doubling. The bacteria see the danger. They search for new bottles and find 3. They assume that their problem is solved. By 12 noon, the first bottle is full. By 12:01, the second bottle is full. By 12:02, all the bottles are full. This is the problem that we face due to the doubling caused by exponential growth. When humanity began to use coal and oil as fuel sources, it experienced unprecedented growth. Even low growth rates produce large increases over time. At a 1% growth rate, an economy will double in 70 years. At 2% rate, doubles in 35 years. At a 10% growth rate, an economy will double in only 7 years. If an economy grows at the current average of 3%, it doubles every 23 years. With each doubling, demand for energy and resources will exceed all the previous doublings combined. The financial system is built on the assumption of growth, which requires an increasing supply of energy to support it. Banks lend money they don't have, in effect creating it. The borrowers use the newly created loan money to grow their businesses and pay back the debt, with an interest payment which requires more growth. Due to this creation of debt-formed money, most of the world's money represents a debt with interest to be paid. Without continual, new and ever larger generations of borrowers to produce growth and thus pay off these debts, the world economy will collapse. Like a Ponzi scheme, the system must expand or die. Partly through this debt system, the effects of economic growth have been spectacular in GDP, damming of rivers, water use, fertilizer consumption, urban population, paper consumption, motor vehicles, communications and tourism. World population has grown to 7 billion and is expected to exceed 9 billion by 2050. On a flat, infinite Earth, this might not be a problem. However, as the Earth is round and finite, we will eventually face limits to growth. Economic expansion has resulted in increases in atmospheric nitrous oxide and methane, ozone depletion, increases in great floods, damage to ocean ecosystems, including nitrogen runoff, loss of rainforest and woodland, increases in domesticated land, and species extinctions. If we place a single grain of rice on the first square of a chessboard, double this and place 2 grains on the second, double again and place 4 on the third, double again and place 8 on the fourth, and continue this way, putting on each square twice the number of grains than were on the previous one. By the time we reach the final square, we need an astronomical number of grains. 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854,776,000 grains. More grain than the human race has grown in the last 10,000 years. Modern economies, like the grains on the chessboard, double every few decades. On which square of the chessboard are we? Besides energy, civilization demands numerous essential resources: fresh water, topsoil, food, forests, and many kinds of minerals and metals. Growth is limited by the essential resource in scarcest supply. A barrel is made of staves, and like water filling a barrel, growth can go no further than the lowest stave, or the most limited essential resource. Humans currently utilize 40% of all photosynthesis on Earth. Though it might be possible to use 80%, we are unlikely to ever use 160%. global food supply relies heavily on fossil fuels. Before World War I, all agriculture was organic. Following the invention of fossil fuel-derived fertilizers and pesticides, there were massive improvements in food production, allowing for increases in human population. The use of artificial fertilizers has fed far more people than would have been possible with organic agriculture alone. Fossil fuels are needed for farming equipment, transportation, refrigeration, packaging in plastic, and cooking. Modern agriculture uses land to turn fossil fuels into food and food into people. About 7 calories of fossil fuel energy are used to produce 1 calorie of food. In America, food travels approximately 1,500 miles from farm to customer. Besides fossil fuel decline, there are several threats to the current system of food production. Cheap energy, improved technology, and subsidies have allowed massive fish catches. Global fish catches peaked in the late 1980s, forcing fishermen to move into deep waters. Nitrogen runoff by fossil fuel-based fertilizers poisons rivers and seas, creating enormous dead zones. At this rate, all fish populations are projected to collapse by 2048. Acid rain from cities and industries leaches the soil of vital nutrients such as potassium, calcium, and magnesium. Another threat is a lack of water. Many farms use water pumped from underground aquifers for irrigation. The aquifers need thousands of years to fill up, but can be pumped dry in a few decades, like oil wells. America's massive Ogallala aquifer has fallen so low that many farmers have had to return to less productive dry land farming. Additionally, the use of irrigation and fertilizers can lead to salinization, the accumulation of salt in the soil. This is a major cause of desertification. Still another threat is topsoil loss. 200 years ago, there were 6 feet of topsoil on the American prairies. Today, through tillage and poor practices, approximately half is gone. Irrigation encourages the growth of stem rust fungi like UG99, which has the potential to destroy 80% of the world's grain harvest. According to Norman Borlaug, father of the Green Revolution, stem rust has immense potential for social and human destruction. The use of biofuels means that less land will be available for food production. An area has a finite carrying capacity. This is the number of animals or people that can live there indefinitely. If a species overshoots the carrying capacity of that area, it will die back until the population returns to its natural limits. The world has avoided this die-off by finding new lands to cultivate or by increasing production, which has been possible largely thanks to oil. To continue growth, more resources are required than the Earth can provide, but no new planets are available. In the face of all these challenges, global food production must double by 2050 to feed the growing world population. 1 billion people are already malnourished or starving. There will be challenges in feeding over 9 billion in the years to come, when world oil and natural gas production will be in decline.